Okay, so now you probably want to know a little bit about the exam. The exam, I've never had the exam so early before. Thank God we did this early schedule thing. Or we would be covering new material on Friday and it would be on the final on Wednesday. That would not be popular. Okay, so this is already online. You can write it down if you want. You can take pictures if you want. Maybe they're pictures of me, I don't know. But this is already on campus, on the lecture notes. So you don't really have to write it all down. This was our initial sketch of what the final exam is going to look like. I'm not saying we're bound to this. This is the 3 instructors writing it, said, let's just lay it out like this. Okay? So it is comprehensive, and we're actually going to write it in like literally 2 parts. It'll be like 2 exams. I don't like that in terms of style. You know, it's kind of ugly, but I think it's mentally better for you. Okay? This is the part where I need to know the old stuff. This is where I go to the first equation sheet. So I think it'll be a little better. Okay? So a regular midterm has 8 multiple choice. So here even though it's 50% more, that would be 12, but we're not going to quite do 12. We're going to do, I think, 11, 1 less than 12, right? So 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? So go a little bit more time. Usually it would have 3 free response, so 1.5 more for a half more time would be 4.5, and we've got 1, 2, 3, 4, 5. But they're free response light. Okay, they're not going to be as long and hard because it's the final exam, especially the ones from the old stuff. So they're all free response light. They won't have, G parts. That's the idea. So it's a little bit less in length than the equivalent midterm exam. That's the plan. Might all change. Who knows? Who knows? It won't change for the harder. I don't know. We got to write it. Okay, so what we're going to do today is just start with the old stuff. So you remember, like, for example, say exam 1, waves and optics. There'll be about 3 multiple choice on waves and optics, and there'll be a free response, light. And then from exam 2, about 3 multiple choice, electrostatics and circuits, and a free response, light. And then this kind of breaks into magnetism, which is actually sort of a bigger topic than these 2. So like this is 1.5 multiple choice. It'll probably be 2 up here and 1 here, and maybe even just 1 here. I don't know. It'll somehow divide up like that. Okay, so when you're thinking about what to do, there's some idea what to do. So what we're going to do first is do a few problems in exam 1, waves and optics. So I spent a while writing exam problems just to give away now. These are the good ones. Now I've got to use the bad ones I can't think of on the exam. Oh well, that's just life. Here is someone texted me a picture. Stop to think. Okay, I don't know. Yeah, this is completely unrelated. I don't know what that is. Okay. Maybe they're just telling me to stop to think. Hold on. Okay, I'm going to rearrange this whole lecture. Okay. So remember section 1, standing waves, right? Frequencies for strings and columns of air. There was the fundamental mode, m equals 2, m equals 3. Wave speeds, all that stuff. Standing waves. Interference is 2 sources. Right? So if you have one thing, it's probably a standing wave problem. If you have 2 sources, it's probably an interference problem. Getting that phase difference, is it constructive, destructive? And then physical optics, of course, is light and a glass and diffraction interference, and then this. How do we get all that in? You're about to find out. Okay, I'm about to show you some examples of multiple choice and free response that would cram all this in, all right? So I'll show one, and then I'll give you a second to think about how you might start it. We don't really have time to do, like, the entire exam. This is all on Canvas, so just do it for now. You have it written down for later. My notes are also on Canvas. These are the answers, right? So for example, and also have ones here that are examples of how you will mess up, how you can overthink it. So let's look at this one. Clamped metal wire supports traveling waves at 50 meters per second. That's really fast. By about what factor would you increase the tension to get the traveling wave speed equal to the speed of sound in air? And it's one of these sort of quick calculation multiple choice. Or maybe you can use your intuition if you've got really good intuition. And remember, so think about that. Just think, what would I do here? And let's look at the formula sheet you're going to have. I forgot to open here. Let's go back to exam 1. Yes. Let's go back to that formula sheet and say what was going on here. And you'd say, well, what did I know? Let's see. Remember, there were several speeds to think about. There's the speed of a wave on a string. There's the speed of sound, which is a constant. The speed of, basically, normal conditions. Speed of light is a universal constant. And then every wave, if you're looking at the relationship between frequency and wavelength, for an individual wave, you can always use that equation. So you got to decide, what are we dealing with here? So if you are, okay, so everybody think for a minute. What would you do with this problem? Let's go back to it. I'll give you one more minute to think before I start blurting out the answer. There's the answer. Right, here we go. Right. So I think you could look at it and start to get confused and say, wait, it says a metal wire and not a string. Oh no, wait a minute. Maybe we mentioned that the speed of sound in metal is much higher than the speed of sound in air. Maybe this is a speed of sound problem. I think there's a formula related to the density. No. Okay, it's easier than that. I just made it a metal wire because it's a really fast wave. I mean, I would have trouble believing that a wave on a string could go with the speed of sound. So we just want to say, can you make the mental jump between a stretched string and a stretched thin wire? That's just kind of, if I say a string, I worry people would say, oh, a string can never go that fast. Let's throw this question out. So I made it a metal wire, but it's still the same thing. It's still just a little pulse moving down the wire. Right? And then if you're confused, I don't know if I should think about the speed of sound in a metal or I should think of it as a pulse going down the wire. You could also, if you really want to torture yourself, you could remember the speed of sound in a solid like a metal is a lot higher than the speed of sound in air. So there's really nothing we're going to do to increase the speed of sound in the metal. Okay? So if you didn't think about the speed of sound in the metal at all, you're fine. I'm just trying to point out where your brain could go off on some weird tangent and panic for 10 minutes. Okay? Look at the equation formulas. We asked for a tension. Only one of them has tension in it. Right? That's the one you want to use, the one with tension. Tension will not affect the speed of sound. We didn't derive an equation for the speed of sound. So I'm just trying to think about how you could, you could kind of get confused. Don't make it more difficult than it is. Right? So you would go to your formula sheet and say, oh yeah, well this is the one we got to use, the square root of T over mu. Right? Tension over mass density. It's the only speed formula with tension in it. And we're asked about tension. But then, so if you can get over that, if you can accept that this wire will act like a string, you've got the right formula, and now your chance of getting it right depends on how algebraically sophisticated you are. So, what you want to realize is we have one condition, you're at 50 meters per second, and we want to get it up to another condition, 343 meters per second, which is on the equation sheet. Right? And we have an initial tension and a final tension. So what you'd really want to do is say, okay, I got my 50 meters per second is the square root of the initial tension over the mass density. And then you might panic and say, is the mass density going to change? But I think several times in the homework and pledge we said you stretch it a little bit, but the mass density is basically the same. The mass density doesn't change that much. I mean, technically you lengthen it, you change the length slightly. But notice I do say approximately somewhere in here. Approximately what factor? So yes, there will be a teeny change in the mass density, but we told you to change the tension. We never mentioned the mass density. Right? It's a wire. It's a solid wire. We're not going to stretch it so hard we change its mass density. So you look at that and say, okay, that's the initial. Now, what are we doing? Oh, yes, if we increase the tension, this will go up. So let's say we increase the tension to get this to 343, which is on the equation sheet, the square root of tension final over mu. So you could write that, and you could say what they're asking is by approximately what factor would you increase the tension to get the traveling wave speed equal to the sound air. So you need to get it where it's like T final equals some factor times T initial. Right? That's the equation we're trying to get. I don't want it. There's no letter I can put that make everybody happy. C. You can ask me what C is later. Text me. C is what we're looking for. So we want to get this in this form. Right? So it's just, what's your deal? Do you love algebra? I mean, if you're really like, you like to do the details of algebra, you could solve for mu. Okay, let's solve the first one for mu. Mu I would solve for this. Well, no, I'm trying to not be sophisticated. I'm not going to solve for the square root of mu. I'm going to say mu equals mu. I'm going to say mu equals, bring it up here and this down here, and it's T over V squared, right? T naught over, oh, here we go, sorry. Ti over 50 squared. All right, that's one way to write mu. Okay. And then plug it into here. Good Lord. Okay. All right, so plug mu in, right? Mu in to this one. and say 343 squared, I'm going to square everything, equals TF, the final tension, over, what was this? This was the initial tension over 50 squared. Ti over 50 squared, right? Right? It was in the bottom of there, so it comes to the top of there. And then you can just say, oh, I'm looking for this. I want TF, the final tension, equals 343 over 50 squared times the initial tension. And there you go. The answer is 343 over 50 squared. Okay? So it's the ratio of the tensions, but you have to square it because the speed goes as the square root of the tension. So that would be kind of the awkward way to get there. A more direct way would be to realize, you can take the ratio of two equations. If A equals B and C equals D, then A over C is B over D. So you could just ratio these. 50 over 343. Now let's put this one on top and this one on bottom. 343 over 50 equals this over this. What's going to happen? The mu's are going to cancel. This over this is the square root of TF or the square root of TI. All right? And then you just square both sides. Squared. TI is that TF. Okay? So there's quick ways to get there. But if you want to do the long algebra, you'll get there too. You're more likely to make a mistake doing this. But that's it. So it's not meant to be a long calculation. It's a multiple choice. 47. So you think you could have done that. That's the question. How much review do you need to be able to do that? That's what you got to ask yourself. I think if you really were solid with that material, just making the pledge problem 5 where you write out your little thing and having the equation sheet is probably enough. A little review might be a good idea. Let's look at another one from that section. So there was your example of a string. Now let's do an open tube. Oh, this is an example of a free response. Yes. And it needs a drawing, so I didn't draw the drawings in PowerPoint. All right, I'm going to draw the drawings here. But you'll have this. Let's see. So the drawing that would go with this would look something like this. Open tube. Remember, we used to drew like this. Open on both sides. Tube of air. And we're saying that it's 30, but we say 10 from each side. There's a slot, kind of like this, kind of a slot like that. And you're sticking like a little solid or a solid disc in here. And it's on a little paddle like that. And you can move it back and forth from A to B. And if you read the geometry of the problem, this is 10 centimeters, this is 10 centimeters, and this is 10 centimeters. Like that. So you're blocking it here, or you're blocking it here. Okay? I used the word diaphragm the first time I wrote it, because in optics that would be a diaphragm. And I decided, oh, that word's too confusing. Too many meetings. Let's not go with diaphragm. Let's go with solid disk. I don't want to make this another vocabulary test. Okay, so the first question is, what are the fundamental mode frequencies of each side at the point shown? Because you're blowing on them, so you're making them make their little sound, right? So the fundamental mode frequencies. So for part A, left, right. Fundamental mode frequency, what is it? Oh, well, the formula is on the formula sheet, right? You don't have to have it memorized. It's, what is it? It's the speed of sound over 2 times the length of the tube. Oh, wait, wait. We got to do it for open, closed. You also have to, yeah, remember, that's the point of this. You have to figure out if it's open, or open, closed, or what is it. So we better go look. Clamped, open, or open, closed. My notes are wrong. It's open, closed. So it's FM, so the frequency, F. What does fundamental mean on this equation sheet? It means 1. It means the first one. Right? So F1 is the speed over 4 times the length times 1. So it's 343 over 4 times what's here, 0.1. So you'll get an answer, and I put it over 2 because I thought it was open closed. And you'll get about half of that. Oh, crap, I can't divide it by 2. 852 hertz. All right. And then on the right side, how long is it here? 20. So the F, 343 over 4 times 0.2. 343 over 0.8, half of that, 429 hertz. And you're done with part A, right? Nothing's happened yet. You just got to realize that it was an open tube, but this thing blocks the air, so it's two open closed tubes. There's the physics. Beautiful. B. These are so gorgeous, I should just put them on the exam. I could be done writing my part. Let's see. So let's see what was question B. Qualitatively describe the beat frequency you hear as you move the wall, or the disc, or whatever I called it, from A to B. So you and your friend are blowing on it, and it's making two notes, right? It's making two sounds, 852, 429. What's going to happen as you move from A to B? Think about it for a second. You guys are really up on it because I'm not getting any questions. Well, oh, I am getting questions. I couldn't hear them. My phone isn't notifying me anymore. Let's see. Yeah, why is it open close? So I just said that again. Yeah, so it's the ends are obviously open because they're open, and this thing is acting as a barrier to block the air. Therefore, that makes it a closed tube. So here I described it as a movable solid disk. All right, now we're getting some questions here. All right. What if you had two disks? It depends on where they are. It would depend. How do you know the disk was 10 centimeters from the left end? I thought it said that. Let's see. A, 10 centimeters from an end, and B, 10 centimeters from the other end. So points A and B are 10 centimeters from each end. All right. Okay, so so hopefully maybe you've thought about what is the beat frequency going to do. So when you're here, why are the different frequencies on each side? Because the lengths are different. It's an open-closed tube that's 10 centimeters. It's an open-closed tube that's 20 centimeters. Different length tubes will have different modes, different mode frequencies, because there's an L right here. F is V over 4L times the mode number. So 1, and the lengths are different. Oh, now we're waking up. But the question doesn't say what the point shown is. What? A 30-centimeter open tube has a slot with a movable solid disk from point A to point B, each 10 centimeters from the ends of the tube. You're going to be gone for the summer. We're not going to be able to argue this, so I'm going to win. But I'm pretty sure 10 centimeters from the other end, I think it's there. This may be somebody in another class. Can you dye your hair purple? I would only dye it green to be the Joker. What about bioelectricity? What about bioelectricity? How did you know the disc? Okay, here we go. Oh, that's from Beer Bike Week. These are old. Okay. Let's keep going. So hopefully you've thought about the beats. So I would answer this like this. Very fast. I mean, you should probably write a little bit more. Through 0, and then very fast again. Right? Because what's going to happen? These two frequencies aren't even close. You're not really going to hear a beat. This will be some beautiful tone, some harmonic whatever. Oh. But as it gets about here, suddenly the two lengths are about the same. The frequencies are about the same. So then you're going to hear a beat. Right? When it's just off the center, the frequencies are within a hertz of each other. So you're going to hear a 1 hertz beat. When it's in the center, the beat frequency will go to 0. Because it's two tones with the exact same frequency. The beat is the difference is 0. So this happens at the center. And then it'll speed up again. Right? So that's the physical insight. Can you visualize these two tubes getting longer and shorter and it going through 0? C. Right. What is the fundamental mode frequency of each side at the point of minimum beat frequency? So I worded that way for if somebody didn't get this and they didn't understand that the beat went to 0, it wouldn't give it away. Right? So even if you didn't realize it goes to 0, it just goes to some minimum. What is it on each side? It might help someone get B. If they didn't get B, they'd start thinking about C. Let me just finish it and we'll answer these questions. So what is it? Well, that's just when it's at the center. L equals 15 centimeters on the left. L equals 15 centimeters on the right. So they're going to be the same, and the frequency is going to be 343 over 4. They're still open-closed. Over 4 times 0.15, which is half of my answer because I did the open. I'm an idiot. No, I'm not an idiot because you'll make that mistake too. We're all doing our best. 572 or something like that. If you printed out these notes already, yeah, I'll fix them soon. There you go. Could you do that? I think you could. Right? Think about how much would I need to study to be able to do that problem. Let's see. Okay, few questions on this one. I'm confused on the very fast thing. Fast? Oh, the very fast thing just means, like, beats are like, if the difference is 2 hertz, it's wah, 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 wah. If the difference is 10 hertz, it's wah, 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 wah. If the difference is 400 hertz, it's right. It's like a 400 hertz beat. I can't do it. That's what you won't even really hear a beat. You'll just hear 2 tones. It'll sound like a saxophone or something. Okay. So why 0 in the center? Why does it start off fast? Yeah, it's because the lengths are different because the frequencies are different. Okay, so just work on it. Or ask in office hours. Let's see. Oh, this one. Oh my God. I got so many different areas in this one question. So beautiful. Let's see. Okay, so moving on to physical optics and light, etc. So this one I'll show you how to get it, the hard way. But if you just remember the chromatic error, aberration diagram, you would immediately be able to answer it. Let's see. So read it there. Dispersion in glass, right? Yeah. Okay. Question part A. Yeah. Dispersion. I think somebody's answering somebody else's question in the text. Y'all can't see each other's text in here. I'm not sure what you're doing. Okay. Dispersion in glass causes light to travel slightly increasing speed with increasing wavelength. Right. So first you got to think back. Okay, I remember how it works. Light goes at the speed of light c, but light in glass goes at c over n. And if you don't remember that, it's on the equation sheet. Right there under glass. Speed in a medium is c over n. So you want to say, okay, what dispersion means, I should put it in quotes, we didn't really talk about it that much, is that it does depend on wavelength, and that's why a prism works and Pink Floyd and all that. Right? So we did talk about that. So we just want to know, if you send white light at a lens, how do the red and the blue focus different? Okay. So the way I would recommend setting this up, you can do it how you want, is I'd put a column for blue and a column for red. Because you've got to get from the statement of how fast light travels all the way to how a lens focuses light. So you've got to think about a lot of different properties. So we're just going to think about it for blue and red as we go down. Okay? So first, what's the wavelengths of blue and red? Which one's smaller? Which one's larger? Blue is like 400. My famous wavelength chart. It's still there. Okay? But it won't lead you astray this time. I think you can tell that blue is at the left side and red is at the right side. So blue, the wavelengths are smaller. Red, the wavelengths are larger. Let's now do speed then. So speed, that was given in the problem. Speed said increasing speed with increasing wavelength. Right? So the red light must be faster. And this must be slower. Remember, there's just a multiple choice, so you're not supposed to do a lot of calculation. And you say, okay, once I know that, I must know how the index changes. Because it's the index that determines how the lens works, right? The index of refraction. So the little bit of a difference you can get because you have this, right? You look at this and say, okay, if it's slower, the index must be bigger because it's in the denominator. And here it must be smaller. So blue light has a larger index than red light. What about the focal length of the lens? You're going to eventually need to know that. F of the lens. Oh, okay. Now we need the lens maker's equation, which is in the equation sheet. Right? 1 over F equals the index of the lens minus the index of the medium over the index of the medium, 1 over R1 minus 1 over R2. Oh my God. Right? You don't have to calculate it. You just have to look at it and know which one is going to have a bigger focal length and which one is going to have a smaller focal length. Someone is asking, doesn't wavelength in glass also change? Yes. But remember, we don't talk about it. We never calculate it. We just acknowledge that it does. But even if these both change, this one is still bigger than this one. And we're talking about a teeny change in the index, so it's not enough to make a difference. I'll address that at the end in a minute. Okay, so we look at this and say, well, if the index of the lens is bigger, it's going to make this bigger. Right? It's just the index of the lens minus 1 over 1. So really just sticking the index of the lens right there. Right? So this must be, oh no, I'm sorry. This number will be bigger, but F will be smaller, right? So F is lower. I wrote lower. F, I'll just write lower. See, I tricked myself. Lower, larger. That's a bad pair of comparatives there. Smaller, larger. Right? Everybody sees that. So a big N means a big number that you have to invert. All right. So finally, then we can imagine what would happen. White light comes along. White light is a combination of all the colors. Right? And red. And what does light do when it goes through a lens? If it's collimated, it means parallel. I shouldn't use the word collimated. It'll focus to a point. And if this has a longer focal length, then the red will go down here, and the blue will go down here. All right. So then the answer is red light focuses closer. No. Blue light focuses closer than red. Yes, it's B. All right. C and D sound like what you might determine if you decide that the index, or that it could be such a big difference it can make the lens negative. You know? But that's why we said slightly increasing speed. So that was the idea, and something you would know from reading the book, that the change in N is very small compared to 1.5. We're talking 1.5 and 1.49. And then mathematically, there's really no way you're going to get a negative F out of this if these are trying to make it a converging lens. This would have to be less than 1. And you know from all the materials we talked about, air is 1. All the materials are above 1. There's no index that's below 1. So it's not like index smaller could have gone to like 0.5. Like that physically just doesn't happen. So there's a little bit of just sort of understanding and knowledge of all the various values. Or you go back to the rule, don't complicate things. Okay? Don't think, well, what if N was negative infinity? Right? Don't do that. Right? Slightly increase with speed. These are small changes with N. Right? Every word means something. Okay. Let's answer these and then do the break here. Is the index a property of the material it passes through? Why would blue have a bigger index than red? Index is a property of the material that depends on the wavelength of light hitting the material. So yeah. Why does blue light travel slower? Oh, I don't get into it. It's too long to explain. What is NM and NL? Yeah, so this is the index of the lens. So this, and I wrote it this way because this is how it's on your formula sheet. So you need to be familiar enough with your formula sheet. Index of the lens material and index of the medium of air. But sometimes we put the lens in water. That's why I didn't put air. But for a lens in air, this is 1, and this is about 1.5 for glass, but then we're having it vary a little bit here. There we go. Oh, there's the interference one. Okay, so since I ranted so long at the beginning, we'll have time to do that and the electrical ones, and we'll see how far we get. Okay, let's take our break. Okay, I got 2 questions that made me say things in a different way that might be useful to help you understand. So one question was, again, why is it this can't go, why are C and D wrong? So C and D, you should say, oh, that would be the case where if one of them became a diverging lens, and that's where F is negative, and you might think, well, this could become negative if this gets small enough, and like I said, it can't, because we're in air, this is 1, nothing goes below 1. But I just want to remind you that you might say, well, then why could any lens ever be diverging? How do you ever get F negative? Remember, it's in here, right? This is the geometry. The definitions of R1 and R2 are what drive the lens to be converging or diverging, right? So not this. This will always be, well, okay. If you put it in a high index medium, it will always be 1. But just in air, this will always be bigger than 1. This will always be positive for just glass and air, okay? So yeah, if you're worried about this being negative, remember, that's in here. And they were both going through the same lens. They were both going through a converging lens. The other question was, now wait, what about this? I thought, wait a minute, the light slows down, but I thought light went the speed of light. So just remember, in air, before it gets into the glass, if this is the glass and this is the air, then both red and blue go the speed of light. Okay? So they're both going at c. C over 1.0, they're going at c. It's when they're in the glass that they go different speeds, and that's what causes them to bend at different angles. That's the reason there is dispersion, is because one of them slows down more than the other. So with lots of fancy optics and diagrams and geometrical optics, we could sort of show you that geometrically. But it's the fact that their speed is only different here and not different here. That's the reason they refract differently, fundamentally. But yes, they were going the same speed before they went into here, when they were in the air. They were both going at speed of light. Okay, let's see. Is this encouraging or discouraging? Not uncertain. Cool. Okay, let's move to the next one. So we got one more in the exam 1 section. And this is the interference question. So we did all of optics with that question. Here's an interference question. And you think interference is the classic. We got to think about the difference in phase. This is in the formula sheet. It's like you got two things, and what was it? The difference in phase tells you if they're constructive or destructive. It's how the difference in their distance to the point where you're observing over the wavelength times 2 pi. And then they might have a difference at the very beginning. I forgot what symbol I used there. If the source has a phase difference. I think I called it phi naught, maybe. Okay. So that's usually your phase equation. And that's what we have here. 2 speakers at 1 meter or minus 1 meter. So on the exam, we might draw it for you. Or we might just give you that. I don't know. But I'll draw it here. All right, I'd draw it and say, there's the origin. Sounds like my detector is at the origin here. And I've got one speaker blaring at a position of 1 meter, negative 1 meter. And I've got another speaker blaring at a position of plus 1 meter. That's what they're saying. And I'm listening at the origin. Right? And what's going to happen is the speakers are going to move out further, all the way to 3. This one's going to move at some speed, and it says they're moving at the same speed. So you're sitting here, you're at some interference condition, they start to move, and it's kind of like those problems when you walked around the speakers. How many minima do you get? Right? Do you hear 1 minima, interference minima, meaning destructive interference? Do you get 1, 0, 2, 3? This is for people thinking maybe about the Doppler shift. We'll see. Okay? So if you don't see it right away, it's a little bit of a trick, right? But if you don't see it right away, that's okay. You can just start plugging in the formula, right? How at the beginning, is it constructive or destructive? Let's calculate the difference in phase. Okay, delta x in these problems, remember, that is the difference in the distance from the source to the detector. That is not positions on the x-axis. Okay, so I probably wouldn't have meant, if I might have not tried to make it this confusing. I would probably not put delta x here and label this the x-axis, because this is not 2. This is 0. Right? This is 1 meter away. This is 1 meter away. 1 meter minus 1 meter. Okay? It's not 2. It's 0. 0 over lambda times 2 pi is 0. Plus, what's the difference in their fundamental, their origination phase constant, as a bank would call it? 0. Because the sound waves are in phase. Or the speakers are in phase. So this is also 0. So it starts out constructive. Right? Now, as those two speaker sources move apart from each other, we want to see how many times does this change and become pi. Right? Because if that's pi, then it's destructive. But how many times is that going to happen? 0. Right? It's never destructive. Because if you look at those two terms, well, that's not going to change. That's just the source. It's saying the sources are in phase. And delta x is always 0. Okay? Because they're moving together away from the origin. This one, if this one gets to 2 meters, this one's at 2 meters. When this one gets to 3 meters, this one's at 3 meters. The detector at the center will just sit at a point of constructive interference. And it'll go through none. So the answer is 0. All right. Can you explain what delta x means again? Sorry, but why is the difference? Yeah, not 2. Okay, so let's go this real careful. Let me see what's on the equation sheet. Here we go. We're going to draw this a little extra careful. So that's 1. If you know what it meant, there's nothing to do. You just put 0, move to the next one. But let's look at the phase difference. And let's read what the equation sheet says. Phase difference delta phi delta x over lambda 2 pi plus delta phi naught, where delta phi describes the difference in phase source constant and or differences due to reflections. Yeah, so it didn't get detailed about that delta x. Okay, so what that delta x means, I think maybe the way I wrote it in my notes, I don't remember, is that delta x is x2 minus x1, but those are not positions on an axis. Okay, x2, their magnitudes, is literally, this is x1. Okay, so these are magnitudes of distances. If you remember back to 125, there was distance displacement. I think we described separately. Magnitudes of distances, source to speaker. Okay, so since they're magnitudes, they don't care about the direction. It's just this distance, x1, and then it's just this distance, x2, right? So 1 meter minus 1 meter. It's just put your pencil on the source and draw it to the detector. 1 meter. 1 meter. 1 meter minus 1 meter, 0. Because that's what really matters, is how many cycles of phase do they go to get there. It doesn't care what axis they're on. This would also be true. Here we go. This will cement it. This will cement it in your mind. Yes. This is going to cement it in your mind like a mob hit. Here we go. What if it was right here? The detector was here, and this speaker was here, and this speaker was here, and this is 1 meter, and this is 1 meter, and they move at the same speed, right? Same answer, right? They're still constructive. They're still both 1 meter away. As they move along those axes, they're always the same distance away. The answer would still be 0. Okay, so the fact that they had them along an x-axis is not the same as what that delta x means. See, now we can't even use that, right? I might have used that on the exam. No. Oh, just giving it all away. Oh, wow. Too many at once. Okay, so any questions? Let's see. Questions on that one. Let's see. Is there always a minimum interference at the origin? No. There's not always a minimum interference anywhere. The reason there's a minimum at the origin is because I put them equally spaced from the origin. I could have spaced them where the origin was destructive. Right, so then you're following up with, is there always a minimum at the origin? No. Why is the answer 0, not 1? Right, because remember, we said it's at a maximum, and I said how many minima are detected. If I said how many maxima are detected, it would have been confusing. It would have been like, well, it's the same one the whole time. Is it 1 or infinity? That's why I asked about minima. There are no minima. Okay, so that's why. All right, we want to get finished here. How would you solve the number of minima if they weren't moving uniformly? Then it'd be a hard problem. You would probably put little d equal vt. You'd put little vt's in. You'd have to put like vt here minus vt here and figure out how long it goes and figure out how many times that equals half a wavelength or something like that. Yeah, that'd be like a free response. Let's see. Is the only reason that there is no destructive interference because they are moving at the same speeds? Yes. So no minima. Is there constructive interference everywhere? No. The whole universe is not constructive interference. Just the center in between. So where else would there be? Here we go. Let's turn this into a live lecture here. Where else would there be constructive interference at all times? Along this line. That'd be a good problem. Draw the line where it's constructive at all times, along this line. Because along this line, they're always equidistant, anywhere on this line. Right? And now, in your head, where would they always be constructive in that situation? Along this line at 45 degrees, right? Because then anywhere on this line, they're always the same distance. We have nothing left, Dr. Stinson. We've given everything away. This is just, let's just not have the exam. If you came to this, you get 100 because you learned it all. Yeah. We will need to use kinematics and material from the first semester on the final. It's a prereq. But have I done any kinematics here? No, I have not. So you wanted to do kinematics. I don't want to do kinematics. Y'all were begging me to make them move at different speeds. Let's see. Okay, let's look at the next part of the class. All right, so that was the kind of stuff that you'd want to know from the first section. Right? Not as hard as the first exam. Probably want to review it a little bit. What are the conditions for destructive or constructive? Constructive is where that difference is 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. And destructive is where it's pi, 3 pi, 5 pi, 7 pi, 9 pi. So it's whether it's even or odd pi. Okay, but that's in the book. Okay, so electrostatics and circuits. Breaks into 3 nice sections here. Remember, we started out with fields and forces. Everything was fine. Coulomb's law are used to get forces between point charges. And then if you just lop off the test charge, it's also how you get the field due to a point charge. Either KQQ over R squared or KQ over R squared. 2 Q's means you're getting a force. 1 Q means you're getting a field. Right? And then the other geometries we did were planes and dipole moments. And those formulas are on the formula sheet. And then forces and torques. Right? Also on the formula sheet. So really this is just, can you interpret and make sure you get the directions right, stuff like that. Yeah. All right, so people starting to ask about specific things on the examiner now, so we're not going to answer questions like that. Right? I didn't cover everything in these practice problems, but yeah, everything potentially could be on the exam. If we write it and decide we're going to ignore one thing, we will tell you. Okay, so then there's potential. That's basically the energy version. So you got to define the electric potential difference, how it's related to energy, blah, 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 equipotential surfaces, and how to get the energy from the electric potential difference, which is actually sort of a weird thing. That's actually how we defined it. We defined it in terms of energy, but then people often struggle to get the energy back because they forget that was how we defined it in the first place. Right? So we'll do one of those. And then circuits, of course. What is current? Kirchhoff's laws. Basically resistor capacitor circuits. All right? Okay. So yeah, you just got to know those. At the end of the world, you just studied it. For exam 2, let's see what we've got here. The first one, oh, wow. Which of those will be fastest connected to a battery? So I'm drawing them here on the board because I didn't want to draw that in PowerPoint. Here we go. A, resistor, capacitor. All the resistors are R, all the capacitors are C. B, resistor network. Capacitor. C, same, resistor network. Right, and then, capacitors like that. And then D. And then E. Let's see, 1. There you go. All resistors are R, all capacitors are C. And the question would just be, which one will charge the fastest when connected to a battery? So the little leap you got to make here is, I didn't draw the battery for you. I didn't draw a switch. But we just say, if you connect this to a battery, how fast is it going to charge up? So you just have to imagine the battery in the switch because you've done many of these problems. Right? And then you got to know, what does that question mean? What's going to charge the fastest? Well, hopefully you remember, or you look at the formula sheet and you say, oh yeah, there's a time constant. The time constant is equal to the resistance of the circuit times the capacitance of the circuit, RC. Right? So probably we either want the fastest RC, the biggest time constant, or the slowest. Let's worry about which one of those we want later. Let's just calculate the time constants. Time constant, tau. Right? RC. What is it here? It's RC. Right? Because remember, really it's, R equivalent, C equivalent. Right? This is one of those things where it's confusing. We say the formula is RC, but for this circuit it's 1/2 RC. As we said, the formula is RC, we meant the total resistance, the total capacitance. For this specific one, it might be something else. Total resistance is R, total capacitance is C, tau is RC. What is it here? What is that resistance? It's 3 resistors in parallel. It's R over 3. 1/3 R. Right, if it's R. What is 2 capacitors in series like that? 1/2 C. They follow the opposite rule. Right? 2 capacitors in series, you add them as inverses. So that's 1/6 RC. Right? A smaller time constant than that. What about this one? This is 1/3 R. And then what is 2 capacitors in parallel? It's like one big capacitor, really. So you make it bigger, 2C. So this one is 2/3 RC. Right? What about this one? R times 2 capacitors in parallel is 2C. That's 2 RC. We're just building up these time constants real quick here. That's a 1/6. And then R, and that is 1/2 C. Okay? And if you forgot the rule for adding them up, it's in the equation sheet. Right? Resistors in series and parallel, capacitors in series and parallel, this is a half RC. So you said, okay, I calculated those. What was the question again? The question was, which will charge the fastest? So I think you could just get it from English. The one that will charge the fastest is the one with the shortest time constant. Right? So that's why it's this. If you want to get it mathematically, you would remember that if we're going to plot the charge on a capacitor, you'd have to remember the whole equation, wherever it's going, Q naught, 1 minus e to the minus t over tau. And you'd have to know that the smaller the tau, like it can go like this or it can go like this. Short taus go like that. So if you kind of knew how exponentials behave, or if you just plotted it real quick for yourself, then you could figure out that it's the small number is fast. Short times are fast. I didn't really intend you to do that. I just intended you to say it's this one, the shortest one. Or if you're really good, you could look at it and say this one has got parallel, the smallest r, and this has the smallest c, so it must be that one. All right. Without even calculating, you could kind of look at it and know it's that one. Right? Smallest, 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 kind of big, 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 etc. Right, so that's your circuit. Multiple choice circuit. A little bit of RC. So that could be really quick or take a long time, depending on how comfortable you are with series and parallel. That one's kind of hard, I guess. Okay. Okay, so here is a free response for the electrical stuff. Okay? Let me pull this up. We'll do a free response and have one more multiple choice. And then we can mercifully be done. All right. Let's erase all this. What are the conditions for destructive or constructive? Why doesn't the smallest tau increase the time because it is in the denominator? You just have to look at how exponential functions work. You'd have to plot yourself a few to see it. A small number in the denominator makes the exponent bigger, and a bigger exponent goes faster, is basically the reason. Wait, which one charges fastest? B. B, 1/6 RC. Oh, this one, that's a little line under it there. Okay, so here is an electrostatic free response. Okay, you got a large 1 by 1 meter surface covered with an excess of 1 nanocoulomb. Did I leave it as a nano? I think I adjusted some numbers on this one. Yeah, okay. So a big surface covered with a nanocoulomb. We gave you the area, sort of, and we gave you the charge. So maybe you can immediately think, I could get the charge density. And we're going to put 1 millicoulomb charge 1 millimeter above the center of the surface. Okay, so if it's 1 by 1, that probably means it's a rectangle. But let's look at it in cross-section like this. All right, so there is literally a 1 meter bar. Okay, to scale, 1 meter. You're welcome. Okay, and let's see what we know about it. We know that its area is 1 meter squared. I mean, looking down on it, its area, this is just the thickness. Right? And its total charge, Q, is 1 nanocoulomb, so its charge density is 10 to the minus 9 coulombs per meter squared. Right? That's just the charge Q over the area. And the area was 1, and Q was 10 to the minus 9. So a very small charge density, 10 to the minus 9 coulombs per meter squared. And we put our little thing, really we put it, since this is all perfectly to scale, we put it right there. Okay, but I'll draw it a little higher. There is our 1 millicoulomb charge right there. 1 millimeter above. Okay? So the first question is, what electric field does the that's supposed to say millicoulomb, I changed it. Does the 1 millicoulomb charge experience? I had micro and changed it to milli. So the reason we said this is a meter and this is a millimeter is to get you the idea it's as though it's an infinite plane. Right? So an infinite plane we have a formula for. This isn't infinite, but it's trying to get you to remember if it's a big plane and you're 1 millimeter away and it's a meter long, it's an infinite plane. Right? So for part A, if you just can't remember it, you go to your formula sheet. What's the electric field near a large plane of charge, or an infinite plane of charge? And it's sigma over epsilon naught. Right? So it's 10 to the minus 9 coulombs per meter squared over 8.85 times 10 to the minus 12, whatever the unit is. All right. Yeah, and you get 113 Newton per coulomb. 113 Newton per coulomb. Okay. If it were an infinite plane, that would be the value everywhere in space. But since it's a finite plane, that's the value if you just stay really close to the surface. Okay. So that's the answer to part A. It was just a simple get it from the charge density. Okay, so now the 1 millicoulomb again, charge is released and allowed to move 1 more millimeter. Okay, so there's lots of hints and information in there. It's released and allowed to move 1 more millimeter. So that might already remind you this is a positively charged plate, and that's a positively charged charge. So it's going to be repelled. So basically, we're not doing external work on it. We're letting it do internal work. Essentially, the field is pushing it up. Well, let's see what the question was. Well, there's 2 questions. Could you do kq over r squared? No. Kq over r squared is the formula for the field due to a point charge. This is a plane of charge. We're not calculating the field due to this thing. We're calculating the field due to this thing. That's why it says field is the 1 millicoulomb charge experience. It's feeling the field due to the plate. It can't feel its own field. That's called the self-field correction, which is a bunch of infinities we put into calculations to make them work, even though we don't know why we have to. Okay, we don't talk about that. What? Yeah, millicoulomb. That U is an M. It's a typo. I'm so sorry. I made this 5 minutes before class. That's an M. They're millicoulomb. Doesn't this formula apply to a gap between 2 plates? No. Oh shit, did I forget the 2? Wait, no. So in the gap of a capacitor, you have 2 plates. So it's twice as big. So there's a 2 in there, unless I screwed up. This is sigma. Oh, so anyway, let's keep going. Let's look at the formula. Hey, look at the formula sheet. Wait, is this formula right? Let's look at the formula sheet. Let's double check. Maybe I messed up. Let's see. Oh, probably not. We haven't even opened this formula sheet yet. Exam 2. I don't want anybody to say I got this wrong because Hafner's an idiot and didn't correct himself in class. Let's see. The field due to a charged plane, yeah, sigma over epsilon naught. There it is right there. Unless that's a pair of planes. I'm now too panicked to remember my factor of 2. The book is sitting right there. Okay, so we have a field. Whether it's right or not, let's not worry about it. Let's see. You wanted to review. Okay, but the key, the physics here, is we say we have a field, 113 Newton per coulomb. I'll give it to you. Now, how much kinetic energy does it have, right? So we want to know how much kinetic energy does it gain as it goes from here to here. Did I ask for the speed? No, because I'm not going to make you do kinematics, because I knew people would be upset about doing the kinematics, right? So I just asked for the kinetic energy. So there's 2 ways to get B. The work on the charge, right? The work is the force times the distance. You don't have to do an integral. What is the force? QE, right? The force in the electric field is always the charge times E. So it's 10 to minus 3 coulombs times E, 113, right? There's F. And now D, how far is it going? 10 to minus 3 meters. Right? This is Newton per coulomb here. Okay. So QE times D. And it's just 113 times 10 to the minus 6. So it's 113 microjoules is how much work, that's how much work the field did on it. And if it stopped from rest, it must have gained that much kinetic energy. So the kinetic is 113 microjoules. That's it. Okay. So a little bit sort of kinematics, not really. And then, now there's another way you could have done part B. So if you did it the other way, don't worry. We're going to get to it in a minute. Because now we're going to ask C. What is the potential difference from the starting point to the ending point? Right? How many volts did it drop when it went from A to B? Well, you say, okay, I remember the relationship between energy and potential. And that was the definition, right? I mean, it wasn't mysterious. It's that delta V, the definition of the potential difference, is it's the change in potential energy divided by the charge. Is that test charge idea. The little charge is like the test charge. So we can really just take 113 microjoules and divide it by the charge is a millicoulomb, 10 to the minus 3. Right? Coulombs. And that's 10 to the minus 6. Right? So 10 to the minus 6, 10 to the minus 3 is 10 to the minus 3. So you get 113 millivolts. Right? Except it's negative. Right? It is actually negative because often we just do magnitudes here. But actually, this is delta U, right? We lost potential energy, so it's actually negative. We gained kinetic energy, positive. We lost potential energy. This was internal work, not external work. If this is external work, then the potential would go up. But it's internal work, so the potential went down. Okay? So you're going to lose 113 millivolts. You could also get that from just knowing near a positively charged object, the potential's high, and as you move away from it, the potential gets lower. So you would have to have it drop. Right? Okay, so that's one way to do this one. The other way would just be to start with the voltage. Right? If we say, what is the kinetic energy? Another way to answer that would be to say, well, the kinetic energy would just be Q, the charge, times the delta V it went through. But what's the delta V it went through? So you could get the delta V first. You could get the potential first. Let me just show you real quick. If you want to get the potential first, and I'll answer these questions, we'll be done. All right, you could get the potential first because you may remember that you have the equipotentials, right? And they're flat near a charged plane, like that. So we went from here to here. You'd want to remember that the other way is that delta V is minus E times delta X. If everything's constant, we're not having to integrate, and you move along the field, then that's the formula. So then you would say delta V is what? 113 times 10 to the minus 3. 113 millivolts. Negative. Right? Same answer. Right? Negative 113 millivolts. So you could actually do part C first. If you know a field geometry and you move a certain distance, that's the voltage. It's just this. Right? This really is this long, definition, E dot D X, blah, blah, blah. We're not doing field theory on the exam. So we just went with a one-dimensional version of it. And then once you know 113, you multiply it by the charge and you get the kinetic energy. So you can do either one. Right? Okay, let me answer this plethora of questions, and we'll do last-minute questions. And then we also have Thursday. Oh, yeah, so this energy thing, I knew this would be a problem. Doesn't this formula apply to the gap? How do you know which charge to use for part B? You're never going to use a source charge. All the plates charge is creating the field, and everything else is all the questions are about what does the millicoulomb experience? How much kinetic energy does it have, meaning the millicoulomb? What is the electric potential difference from its starting point? It, meaning the millicoulomb. I would word it more carefully in the exam. Since it's asking about the millicoulomb, that's the little charge. It's experiencing the field. The plates charge just created the field. Once the field's created, we don't even care what the plates charge is doing. Okay. Let's see. Why is potential energy equal to kinetic energy? Basically because delta, so the total energy change here was 0. There was no external work done, so delta U plus delta K had to be 0. Because this work was only really the internal work of the field pushing the charge. So that's why they're the negative of each other, basically. We don't want to get into the whole work thing again. Why is the work? Yeah, to KE, that's why. Is kinetic energy always equal to work? No. So if I have a chalk here, I do work to increase its potential energy. It doesn't have any kinetic energy. So we're not going to write questions where you need a deep understanding of energy balance, except like this. Right? So you don't need a detailed energy balance here. You could also do this kinematics. The thing was accelerated with a force. You could get the final velocity, 1 Fmv squared. Right? I mean, this wasn't meant to be a big energy question. But it's just if you push, the work you do is FD. You're definitely not gaining potential, you're losing potential. So it all has to go to kinetic. Yeah, I can't really say that clearly off the top of my head. Why is it negative EX? That's just in the definition. It really comes from the field theory. It's too long to explain. If you move along the field line, there's a negative sign there. It's from the definition of the potential difference. Okay? So that was a flavor of, I think, roughly how... Oh, there's one more. We'll do it next time. It's a multiple choice about capacitors. No, we'll do it next time because it's very deep. You got to think about it carefully. It's about capacitors.